The next topic is gradient descent, various versions of stochastic gradient descent. Once again, what is the overall backpropagation algorithm? We do the random initialization. After that, let's say if this is input layer, this is hidden layer, if this is output layer, we do the feed forward step followed by backpropagation, followed by error calculation, followed by backpropagation, followed by weight updating. Okay. Now listen to me carefully. If for doing the feed forward and calculating the error, while doing the feed forward and calculating the error, if you are sending the full data, if you are sending the full data and calculating the y actual values, calculating the y predicted values, and then you already have the y actual values, that means you send the first data point, second data point. Let us suppose if you have 10,000 data points, you send all these 10,000 data points, then you will have 10,000 predicted values, then you have 10,000 actual values, then find the sum of squares of errors or some form of the error from I equal to 1 to 10,000. Then you do that error calculation, back propagation, update the weights. That is known as one epoch. This is the original gradient descent algorithm. Listen to me carefully. One epoch means sending one full data once. Okay, one full data is seen by the algorithm. All right. Now there is a new approach that has been proposed. You know what? Don't send the full data. Why? Because sending the full data is taking too much long term, too long time for single epoch. For a single epoch, it is taking too much of a long time, and I have to store a lot of data as well. Internally, system is finding it difficult. The next solution that is proposed is send one single data point. All of you, look at this carefully. Send one single data point. Calculate the y predicted. You already have the y actual. Calculate the error. There is no sum of squares of error. Simple error square. Then do the back propagation. Do the weight updating. That is called one iteration. One iteration. Why it is called one iteration? One epoch means one full stretch of the data. That is one iteration. Then send the second data point, third data point, fourth data point, fifth data point, like that. That means for completing one epoch, how many iterations will be there? Let's say you have 10,000 data points. One epoch means sending all the 10,000 data points. But if you're doing this stochastic gradient descent, what do you mean by stochastic gradient descent? One record at a time. One record at a time. At a time. Sending one record at a time, then updating the weights after each one record. Then how many iterations will be there in one epoch? How many iterations? Think about it. How many iterations for each record? You are updating the weights. One iteration, second iteration, third iteration, fourth iteration, fifth iteration in one epoch. Now you have to understand the difference between epoch and iteration. Iteration means once. How many times you are updating the weights? One updating of the weights is known as one iteration. One epoch means one full stretch or one full data set, one full round of the data has been seen by the algorithm. If you talk about the original gradient descent algorithm, it says you send one full data in one stretch, then do the feed forward, then do the back propagation. This is the original gradient descent. Okay. So in one epoch, how many iterations will be there in gradient descent? In one epoch, how many iterations will be there in gradient descent algorithm? One iteration means one updating of the weight. So in one epoch, how many iterations will be there in the original gradient descent algorithm? One epoch equal to one iteration in gradient descent. Are you with me, all of you? Because you will send the full data, calculate the full error, update the weights. But this is tedious. This is like, especially if you have large data set, then it will be really tedious. Then stochastic gradient descent is proposed. What is stochastic gradient descent? You send one record at a time. One record at a time. Then you do the feed forward back propagation. See, this looks like a problem. I think this also looks like a problem because one epoch will have how many iterations? One epoch will have how many iterations? One epoch will have as many number of rows, those many iterations will be there. Yes or no? Do you agree with that point? I think all of you are answering correctly. As many records are there, those many iterations. See, gradient descent is also a problem. Stochastic gradient descent also a problem. Why stochastic gradient descent is a problem? I think you also agree to this point. Stochastic gradient is also looks like really a problem, isn't it? Updating the weights based on single record. Do you really update the weights based on a single record? No, that is also not a good idea. But sending all the records also looking like a problem. Can you suggest a better method? I don't want to use SGID. I don't want to use stochastic gradient descent. I don't want to send full records. I don't want to send one record at a time. Can you suggest a better method based on this? Intuitively, what do you think? Try to think about it and suggest a better method for me. Maybe neither I will send full n records, nor I will send one record. Maybe a smaller subset, maybe group by group, maybe send 50 records, maybe send 100 records, maybe 50, 100, maybe send 200 records, maybe send 500 records. Neither you send complete n records, nor you send one record, maybe group by group instead of group. That is known as batch. That is known as mini batch gradient descent. Mini batch gradient descent. Do you understand what is mini batch gradient descent, all of you? What is mini batch gradient descent? Sending a batch of records and then doing the feed forward. Sending the next batch, feed forward, back propagation, error updating, and then weight updating, batches. Let us suppose. Now answer this question. In gradient descent, stochastic gradient descent, let's say mini batch gradient descent, mini batch gradient descent. Imagine there are 10,000 records and mini batch size is, let's say, 100. Now, one epoch will have how many iterations in gradient descent? If you follow gradient descent approach, one epoch will have how many iterations? If you have overall 10,000 record, in gradient descent method, one epoch will have one iteration. Spot on. In stochastic gradient descent method, one epoch will have how many iterations? In stochastic gradient descent, one epoch will have how many iterations? In stochastic gradient descent method, one epoch will have 100 iterations. In mini batch gradient descent, if the batch size, now that is in your hand, batch size is in your hand. If batch size is 100, how many iterations will be there in one epoch? In one epoch, how many iterations will be there if your batch size is 100? If your batch size is 100, that means you are sending 100 records. Overall, how many records are there? Overall, how many records are there? 10,000 records are there. Yes or no? Out of them, you send the first batch of 100. If batch size is 100, you send the first batch of 100, then update the weights. You send the second batch of 100, update the weights. Third batch of 100, update the weights. So one epoch will have how many iterations now? So one epoch means one full stretch of the data. One full stretch of the data is 10,000 records are there. Each batch size is 100. Now think about it and tell me one epoch will have how many iterations? Because you have 10,000 records, 100,000. You have 10,000 records divided by a batch size of 100. Yes or no? 10,000 records divided by batch size of 100. Exactly 100. 100 iterations will be there. Do you agree with that point? All of you. Think about it. Each time you're sending 100 records, then 100 records, 100 records, 100 records, 100 records. That is known as mini batch size, mini batch gradient descent. Usually we neither use gradient descent nor use stochastic gradient descent. Gradient descent is not used. Stochastic gradient descent is not used. It is mini batch gradient descent that is used. But for all three of them, The function is SGD only. We use SGD. By default, there is some batch size internally. So let us suppose you are using SGD. So if you are getting confused about the number of iterations in SGD, let's say there are 10,000 records. There are 10,000 records. This is the data whose size is n records are there. N is 10,000. In SGD, one epoch will have how many iterations? First think about it. One epoch in SGD method, one epoch will have how many iterations? One epoch means one full stretch of the data. One iteration means one weight updating. Yeah. SGD has how many epochs? 10,000 epochs. One epoch has 10,000 iterations. Can you tell me why 10,000 iterations are there? Why 10,000 iterations are there? Because you are sending one record at a time, updating the weights, one record at a time. What if you send two records at a time? Two records to update the weights. Then one epoch will have how many iterations if you are sending two records at a time? Two records, two records, two records. You are saying one epoch will have 5,000. One epoch will have 5,000 iterations. Is this calculation clear? Please confirm. Is this calculation clear? Instead of sending two records, what if your batch size is 100? You're sending 100 records at a time, 100 records, sending 100 records at a time. This is known as batch size. Batch size is 100. If batch size is 100, you're sending 100 records at a time. Then how many iterations will be there? If batch size is 100, how many iterations will be there? Have you understood now? Simply what do? Number of records divided by batch size. Those many times the weights will change, yes or no? Have you understood the?
Yes, sir.
Yeah.
Yes, sir. Got it.
Yeah.
Only thing I got confused in when you were mentioning that when you are doing the comparison between gradient descent, SGD,
Hmm.
and mini batch, right, sir? So
Hmm.
there you mentioned 100 for 10,000 records. So that is where I got confused. It should be 10,000, right? For one epoch.
For one epoch, for gradient descent, let us suppose, let us do that once again. Let's say if
Yes.
we have n equal to 10,000, 10,000 records are there. Okay. I'm doing gradient descent method, stochastic gradient descent method, and mini batch size, and batch size is 100. Okay. Mini batch.
Okay, sir.
Now, one epoch will have how many iterations? Now, if we calculate iterations within one epoch,
One.
after one epoch, in gradient descent, after one epoch, we send all the records. That's why after one epoch, only one weight updating, one iteration. This one is clear,
Yes.
isn't it?
Yes.
Nothing to think about it. In SGD, one epoch will have how many iterations?
One 10,000 iterations.
10,000, which means same as n. With mini
Yes.
batch size, you're sending 100 records at a time.
100 iterations.
So you will simply divide 10,000 number of records divided by 100, isn't it? Why? Because you are doing 100 at a time. Yes or no? So how much is this? 100 iterations. Yes or no?
Yes, sir.
Yeah, it's simply batch size need to be divided with the overall number of records, because those many batches will come. How many ever batches are there? Those many weight updates will happen. Okay.
Got it, sir.
Is it
Thank
clear?
you.
Okay.
Yes, sir.
All right. So how do we give this? How do we mention them in the model? Usually mini batch gradient descent is the one that is by default, but it is written as SGD only. But within SGD, there is something called batch size. Batch size parameter will be there. And default batch size parameter is neither 1 nor n. If you keep default batch size 1, then it will be SGD. If you keep default batch size as n, then it will be GD, gradient descent. I think default batch size internally is some 32 or 64 or something like that. Okay. Internally. We can change this actually. We can decide how many number of records that we want to send. Usually it is picked maybe around 5% of the data usually, or maybe 1% to 5% of the data is sent as one batch. That means if you have 10,000 records, if you have 10,000 records, what is 1% of it? Maybe 100 records is one batch. Or maybe what is 5% of it? Maybe 500 records is one batch. You can send these batch sizes. There is no exact way of what do you call optimizing this. You can choose maybe 1% to 5% as the batch size. You cannot give percentage, you have to give it as a number. Okay. So while mentioning it in the code, if you go back to the code, how do you mention it? If it is stochastic gradient descent, so HGD is the same function. HGD is the one that is used. But where do we mention it? Batch size, model dot fit, batch size. Here batch size 1, which is stochastic. If you keep batch size here, batch size, next example, the batch size is set to be somewhere around, how much is the batch size? Let me check. Batch size 256, batch size 128, batch size 100, and all that. My suggestion to you is always choose the batch size to be 1% to 5%. But we have humans, we choose the batch size to be 50, 100, 200, 500, 1000, okay, 2000, 5000, like this. We choose the batch size like this. This is not the better way to do it. The suggested method is give it in the binary way. Okay. What do you mean by giving them in the binary way? Instead of giving batch size 50, give the nearest multiple of 2. Either you choose the batch size as 32 or 64. Internally, it will get even much more faster, because if it is somewhat multiple of 2, internally the memory allocation will be better. Cache will be allocated better way. Then you will have slightly better performance. So if you want to give batch size 100, what is the suggested value that you can give? Tell me. If you want to give batch size 100, but do not give 100, that is not a good method. Think binary always. So instead of giving batch size 100, what is a better value to give? Even if you give 100, that much space has to be allocated, same as the one that is 128, nearest power of 2. If you want to give batch size as 200, how much is the value that you have to give? If you want to give batch size as 200, instead of giving 200, the better value that is suggested is 256, nearest power of 2. Batch size of 500, instead of that, the better value is 512. Batch size of 1000, 1024, like that, 2048, like that. Okay. That is a kind of suggestion that is given by the experts. Once again, everywhere it is SGD only. What really decides whether it is GD, SGD, mini GD is batch size. So here is the model configuration. Once the model configuration is done, while training the model, the batch size will come into the picture. Can you tell me one thing? In the model.fit, if you do not give any batch size, there is a default number that has been considered. Internally, the default batch size, I think it is 32 or something. If you do not give it, don't think it is a complete GD, or don't think it is complete SGD. It will be still mini batch only, because that is what is most useful, most meaningful. Are you with me, everyone? Okay. So go ahead, execute this batch size example. So that is the place where, sometimes you may see batch size as one of the parameter. The story behind batch size is this one in the gradient descent function. The last one is not a hyperparameter, but this is some information that we should know about the loss functions. There are some other alternatives of loss function. Until now, the only loss function or the cost function or the error function that we have used is sum of squares of error, which was working fine for most of the problems. What is sum of squares of error? You have the y actual value minus y predicted value whole square, sum of that is error at one point, sum of squares of errors at all the points. That is the SSE, or mean sum of squares of error. That was the only error function that we have used, or the loss function that we have used. Other alternatives are also available. So squared error loss or squared loss, that is the sum of squares of errors that we talked about. This is the usual squared error loss. Until now we talked about this only. You can take mean squared error, which is not really different. You take the average of the sum of squares of errors, which is known as mean squared error. Mean absolute error can also be considered, MAE. Sometimes it is known as MAD, mean absolute deviation. Instead of taking the square value, take the absolute value. Mean absolute percentage error, MAPE, can also be considered. But the most widely used one that I have seen is mean squared error. Maybe sometimes if you see them, just understand that these are different forms of loss functions. You may not see a huge difference. Instead of using this loss function, if you use this one, instead of using this, if you use this one, you may not see a huge difference. Okay, that may not happen. I haven't seen it in my experience, like completely changing everything based on the loss function. But however, you may have to try these as well. If there is a particular problem statement which is working perfectly with a particular loss function, we can consider that as well. But these loss functions are deviation based. Remember, these functions are deviation based, y actual minus y predicted. These are good for regression problems. They can work for classification as well, no doubt about it, but they are specifically good for regression problems. There is another loss function called cross entropy that works perfectly for classification problem. Okay. For classification problems, this cross entropy works perfectly. This is known as binary cross entropy. What is the formula? Minus y into log of y predicted, 1 minus y into log of 1 minus y predicted. So imagine if it is binary, then let's say you have y0 and y1. Binary output is there. Usually we don't consider y1, y0 and 1 minus y0. That's what we say. Okay, y and 1 minus y. Binary, either 0 or 1. Let us suppose even though it is binary, to generalize it, y0 and y1 are the outputs. Then what is the binary cross function? Binary cross entropy. Y naught into log of y naught predicted plus 1 minus y naught. Instead of 1 minus y naught, I am writing y1 into log of y1 predicted. This is called binary cross entropy. This is another error function. You might ask why it is an error function. Why does this work? How come this is an error function? Why it works better? Okay, let us think about it. Let us suppose if the actual value of y is 0, predicted value is 0.01. Actual value of y is 0, predicted value of y is 0.01. What do you think? Error should be higher or lower? Error should be high or low? What do you think? So if you use the error function, since y is 0 and predicted value is also nearby that, error should be lower. So if you calculate the error value, binary cross entropy, if for this log e, whether you take 10 log 10 or log to the base e, both of them will be lower value. If actual value is 0, predicted value is 0.09, 0.99, 0, and so there is a huge gap. If there's a huge gap, then error has to be higher. In this particular case, error will be higher. Think about it, all of you. Actually 0, but the predicted value is 0.99, error is higher, whether you take log to the base 10 or base 8. Actually is 1, predicted value is 0.01, then again error will be higher. Actually is 1, 0.99 is the predicted value, error will be lower. This is called binary cross entropy. You can take it for multiple classes as well. You can extend this same thing. Till now we have seen only y0, y1. What if I have y0, y1, y2, y3? Then what is the formula? Minus summation y0 log of y0 predicted plus y1 log of y1 predicted plus y2 log of y2 predicted. That is known as categorical cross entropy. You may see something called categorical cross entropy, that is y1 log y1 predicted, y2 log y2 predicted, y3 log y3 predicted, y4 log y4 predicted. So categorical cross entropy is yj log yj predicted, where j is running from 1 to m classes. So sometimes for classification, you may see categorical entropy. Even for classification, you can use sum of squares of error. You can use the other one. But this is a kind of very much suitable for classification problems. Maybe it may work much faster, maybe it may give slight better accuracy. So my suggestion to you would be, if you are working with classification, maybe use the entropy based, cross entropy based error functions, be it binary cross entropy or categorical cross entropy. Okay. If you are solving a regression problem, maybe use a deviation based ones. Even if you mix them up, will it work? It may work, but this is the one that is suggested. As I told you, if everything is fine, we will not see the need of all this. Sometimes when you get stuck in a problem, you will see that one of these hyperparameters or some of these functions need to be considered. That completes our discussion on ANN or deep neural network hyperparameters. As I told you, these are not like rules. These are the suggestions that you may find useful when you are solving the problems. Okay.